Welcome to the course on two-dimensional signal processing, principles and practices. We are doing the 2D Fourier analysis in this week. So, to conclude the Fourier analysis part of DSFT and DFS, also the 1D along with that, we will do some of the codes which can on how do we perform this in the MATLAB. So, here determine the Fourier coefficients of the signal which is given below. So, a signal which is given as x minus 1 by 2, 0, 0, 1 by 2, that is create this array first here in the MATLAB, that what are the sequence, and this sequence is having the period x of n. So, and store the length, that is what is the length of the sequence needs to be known. So, you need to know this is not having the 0, 0 index, it will have the 1, the index will be 1, 1. So, we need to index values accordingly change it when we use it, when we have the real signal, and the sequence when we create in the MATLAB, as you know. This n is the length of the sequence. How do you find the length of the sequence? It's very elementary thing which we can be done. And then we use the sequence here. This is x of n, you can see the periodic sequence of. So, the periodic sequence is having the n from 1 is here, and then minus 1 by 2, 0, 0, and plus 1 by 2. So, you can see 1, 2, 3, 4, 5 here. After this pattern is getting repeated. So, this is the length for which the signal values are different, and after that one is repeating. We can take it from minus 1 by 2 here, that is. So, this is 1 in this direction also. So, this is also repeating. So, this is a periodic sequence. For this periodic sequence, how do we find this DFS or DTFS for it? The MATLAB command we use is generally this FFT. Only FFT is possible to use it for DSFT and then DTFS and so on. So, here CK FFT x by n. So, the x is this and the length of the sequence is n. So, you get the CK coefficient. So, the CK coefficient, you can see the scaling factor used here, and this can be used in synthesis equation as well. So, here it is used in the analysis equation. You can see the FFT of x by n. So, this you get the coefficient and print this coefficient. So, this is to display in the console what are the coefficient. So, we can just use the DSFT and put it in the quote what should be displayed. For k is varying from 0 to n minus 1, the length of the sequence. So, get the format likely the percentage dot 6f percentage plus point fj, and then it is you can have the printed format in this, and then you extract this real and imaginary parts of it. So, what FFT gives is a complex number that can be separated into real and imaginary, or absolute and angle, to get magnitude and phase spectra. So, we can plot this magnitude and phase spectra, or as a real and imaginary part, it can be a that is magnitude and phase plot. So, here this is to extract this, you can see k is real of ck, k plus 1 and k plus 1. This is to adjust the indices where it will not start from 0. So, we have to make it 1 and 1 and so on. So, if k is varying from 0 to 1 and absolute of ck. So, this would give us the case of magnitude of ck, what the complex number we got it from FFT. So, and then we can have this also for the case of plotting ck1. So, we will see this if we say use the angle ck, that would give the phase plot of it. So, what are the commands which are very useful in this case is that you can have this 1D command which we use is FFT of x, and this need not be there 1 by n if you are plotting ck as such. So, it is the scaling factor. So, now getting the plot of magnitude, this is the magnitude plot in which the labels also y label and x label can be given. So, that's not a part of the code. It can be, you can represent it, you can add it, this x label and y label also in the how to create this figure windows. Now, the case of magnitude spectra. So, we got this k, the coefficients for the k. Ck and its magnitude. So it was 0.2, and then here it is in between this 0.3 and 0.25, which we are getting because of this 1 by n divided the scaling we have done in these cases. So we have 1, 2, 3, 4, 5 coefficients. Got it. And then the spectrum would be repeating also because the signal is discrete and periodic, and the spectrum would also be discrete and periodic. So the discrete maps into periodicity, and the periodicity maps into discrete. So these values are only due to the scaling which we had used. So you can get the magnitude spectrum by making this absolute of Ck, and we can also get the next figure window, which you can see the stem plot we have introduced in the some of the codes. Also you can see the angle of C of k. So this is C of k is the complex number. You get the spectrum from it, use the angle, and these are the just properties used for stem, field and line width and 2 and so on. X label and Y label, we get the k, which is the 0 to 4, and then the angle Ck, which is in radians. So you can see the phase plot, which is antisymmetric. Okay. Also the Ck, which is symmetric plot. So this is how for 1D signal we get the phase spectrum and the magnitude spectrum. So we can also plot this real and imaginary, what we obtained in this case. Here the real and imaginary, these two can be plotted with respect to k as well. So k versus real and k versus imaginary. So this is another plot which we get in case of 1D DFS or DTFS. Now coming to the next example of inverse, how do we get the inverse DTFS in the 1D DTFS? The example which we had done in a few lectures back, that determine the signal x of n for the coefficients given. So here when the coefficients are given, so need to specify that Ck and its period. Okay, so what is the period for which this Ck is computed? Okay, so there is n, and here we have used here is n is equal to 8 and 0 to 7, and it can be a repeated one or 0 to, that is it can be from any -3 to +3, or values can be obtained as such. Now Ck is the coefficients what we had is plot the ones 1, n. So set all DTFS coefficients to 1 by n. So it is to these coefficients are 1 by n. So this n is purely depends on the fundamental period what we had, what we had. So now this x of I f of t n star Ck. So this IFT is the command which needs to be used for finding the inverse DTFS, IFFT, and whereas this FFT, this is for one-dimensional sequences. For two-dimensional sequences, this is little different into two, this FFT and IFFT to find the Fourier and inverse Fourier transforms. This is the command used into n into Ck. So this is again the scaling used here to reconstruct this Ck coefficient into x of n e power j 2 pi k n by n. So this assumes the different scaling, and we multiply it to reconstruct it. N should be here. So now how do we plot it? That is -7 to +1, -n plus 1 to n minus 1. So this indices can be 8 to -7 to +7, or 8 to -8 to +8, or -9 to +9. So n is given as 8. So in that case, it can be of -7 to +7. So finding the real x mod of n comma n is not the command which is computing the mod of it, because it is periodic. So it should be it should come under one period, and then the what we get xp, which is the here x, and the x needs to be made it periodic. So that's how it is going to be the n comma plus 1. So x value what we got is made as the indices needs to be mod, and then figure it. So it's filled with, these are the properties that need to be used here, also the x label and the y label things. Now if you get the plot, the signal back 0 and 1, it is again 0 and 2 and all of the values it is 0. So, it is plot from -7 to +7, you can see that, and the 0 at 0 this is 1. So, what we got from here, this IFFT is giving only one signal point at n equal to 0. So, if you look at the coefficient what is given, so this coefficient is having all the frequencies and it is also periodic. So, this all the frequencies, the periodicity until it is defined, we will not come to know that what is the period of this actually. So, if by knowing the pattern of it, maybe from the full plot, if we have CK, it could be identified that what is the period of it. Otherwise, this given the coefficients, always periodicity or the fundamental period will be given. So, for this, if you see, it has all the frequencies. So, if you take the inverse Fourier of it, that is actually the impulse. So, that is what we are getting here, that an impulse at n equal to 0. This is x of n. So, for this one, if you compute the DTFS, then that you would get the CK coefficients, all the CK coefficient. So, you can plot it and then for DTFT of a sequence. So, DTFS and DTFT, we have, this is a periodic sequence, and whereas in the previous case that is a periodic sequence. So, x of n 1 by 4 mod n, here this n, this is a two-sided sequence. So, n can vary in both the directions, -1, -n and +n. So, we have already plotted this sequence. If you recall, this is going to be 1 and then it would be n equal to 1. This is 1 by 4, n equal to 0, it is here, and then 1 by 4 square, 1 by 4 cube, and so on. This would die down as n increases to n is increasing up to infinity. And then here similarly n is having minus values, minus n. Okay. So, this will be -1, 1 by 4 whole power -1, 1 by 4 whole power -2, and so on. So, this is again the sequence, which is because a is less than 1, this would be a decaying sequence. So, this a, which is considered to be 1 by 4, and the number of points it's up to us that -60 to +60, the n can be varied, and it is -infinity to +infinity. So, it's definitely we cannot plot up from -infinity to +infinity, we need to go for the finite duration here. So, this sequence is aperiodic. So, we have gone for Fourier transform, and this is discrete also. So, this is what DTFT we are doing. So, for x a absolute of n, that is for the if you take absolute of n, here there is a frequency samples defined. This samples again it's not, it can be defined for any values of this, for smoother value. So, what we do for the computation of DTFT. So, first this inner one, which is FFT of x comma m. So, m is a point which we have used, that is 4096. It can be the length of any value, because we at least some point of time we have to truncate the sequence. So, as far as possible we have used so much sample of 4096. So, this if you compute only FFT x, so that would give the FFT of it, and this FFT shift, how, let us see how this is useful. FFT shift of that, so we create a lin space from -pi to pi, and m is the point in 4096. So, it is a linear space created using the lin space, the command. So, from -pi to +pi, where w are the omega, we plotted, used for plotting. So, this is 4096 plots, points can be taken in the -pi to +pi definition. That is, in the area of -pi to +pi, you can get number of points as 4096. After this w, plot is w versus, because the DTFT, discrete time Fourier transform, where the signal is discrete and aperiodic. So, aperiodicity maps into continuous, and this you would get omega continuous. That is why we are creating the lin space, which is of m points from -pi to +pi. So, we are not going to plot as like in the n, only having the discrete spectra, whereas here this is going to be, the spectrum is continuous. So, the absolute value of x, what we got here. So, this plot will be, otherwise this would be the shift would give the plots, I mean shifted plot, but the absolute value of x, this whatever the value we have, it is complex, and this complex value we get the magnitude alone. So this is the x-axis of magnitude, and phase can also be plotted by taking the angle of x. Okay, here we are showing only the magnitude plot where it is with respect to 0. Omega is with respect to 0, so we get here from -2 or -3 to +3. This is from -pi to +pi, where the value we have plotted this. We can this plot will be repeating or not. That is because this is continuous because of aperiodicity, and discrete maps into periodic. So the signal is discrete, so it will be mapped. So this would be repeating, as we have seen in the DTFT. This would be repeating, so that this continuous pattern would be repeating. So, but we restricted this pattern to be -pi to +pi. That is to show it here. This is a magnitude plot, and phase plot we can plot as well, and omega. This F shift, it helps in keeping it at 0. So that's the FFT shift can be used, and you can see the plot without FFT shift also. That would be here somewhere. So this is from -pi to +pi to make it the plot between -pi to +pi. This is done, and the magnitude is taken with absolute of x. So again the FFT command is used, and for continuous samples you need to know x, how many sample FFT you are calculating. This is 4096 because of fine value of omega we are going to plot. If we have the discrete and stem plot, you would get that in the as discrete plots, but what we get is this here is the for omega continuous one. And then we move on to the next example of this DTFT, in which given DTFT is this cos square omega. It's again to get this DTFT, inverse DTFT. So get the plot n equal to 7. That is for this, again when we go for inverse Fourier transform, this n needs to be specified. Okay, so whether it is discrete, what amount of n for which it is obtained. So n is 7 and k is from 0 to n minus 1. These are the index value in the Fourier frequency domain. So omega, which is 2 pi k by n, we know that here 2 pi k by n, and the signal is given is cos square omega. Okay, so this is the x of e power j omega which is taken, and now compute the IFFT of x. So this is 1D, we have this inverse for Fourier transform, getting this signal back, that is x. So if we use this omega for here, what would be the real case, real value of x? We can even take the real part, and for plotting this FFT shift is used to move the zero frequency component to the center. So that's n. Because n is odd or even, that needs to be taken care, because n should be an integer value in the plots. So what we have, because x of n discrete sequence is defined only at integer values. So if it is n by 2, if it is odd value, then it would yield fraction, so that is not applicable. So when you are plotting, you need to use this ceil command of if it is n equal to 7 and all. So n x plot, and this is the property of stem, and give the labels n and xn and get the IDTFT plot. So in this n, and this is 0, at 0 it is 0.5, and 1 it is 0, and minus 1 it is 0. This is for one period, 2 and -2. So here this can be varied as well, depends on n what we have, what we get. This sequence x of n gives the cos square omega, where the Fourier domain magnitude or the coefficients been given here, or it is going to be the example of which we had done in the 1D case. This example we took, and we found that there are two impulses of cos omega and cos omega, and so this is the two impulses you can see at these points at omega here, and then we have this DC which is due to the cos square omega. So if you have only cos omega, you will have the two impulses at a particular point. So this we had done analytically as well, and this we during the this process MATLAB code, we had doing it with the MATLAB codes. How do we write it and how do we get these plots? And then coming to the DSFT, which we had done in the previous lectures, that 2D sequence. So taking the x 2D sequence, which is having the 3 by 3 matrix, and this 3 by 3 matrix should be represented in a sequence like this. So this was the sequence n1 and n2, 1 by 6, 1 by 3, 1 by 6, 1 by 6, 1 by 6. So this sequence, now if it is separable, it is easy to get this plot of DSFT which we had seen already, and we just get the DSFT through this 2D DSFT. So H omega 1 omega 2, you can see that how do we get the DSFT? The command is just frequency 2. So all two-dimensional sequence processing, it should be 2 frequency. For UQZ, frequency response of 2. That represents 2D. So you have to give the sequence, that is what is x and how many the points this needs to be plotted from the 2D to get the frequency response. So figure, and especially to get the frequency response of 2D, so we visualize it in 3D where omega 1 and omega 2 varies, how this real H which is the response, frequency response looks like. So the creating those points, a mesh grid is used, that is omega 1, omega 2 and real H. So omega 1, omega 2 obtained from here. For that value, create a mesh grid and then use the labels. These are only labels. We get the DSFT plot for a 2D sequence where omega 1 is varying and then omega 2 in this direction, that is here 0, 1, minus 1, 0, 1, and we have the frequency response x of j omega 1 or x of omega 1 comma omega 2. This is directly getting the 2D response, 2D DSFT. It's not through the separability. What we have done through the separability also. In that case, you have to use 1D DTFT and then we can plot it also. Combination of the sequence and then take the product of the two and get the 2D DSFT. So this is directly obtaining this for DSFT through the 2D for the 2D sequences. So you can see this is the top and then the surface, which is, and you can visualize this on the other side as well. So the 4 sides of this where it is minus 1 and similarly here 0 0 is 1 and 1 minus 5. So this is a surface plot which we get it for the frequency response, especially to visualize the filter response. It can be a low pass filter, and if it is a high pass filter, that would be a inverse of a plot of that. So this is the for the sequence what we had to consider is the DSFT. And what we had seen in the previous lecture, the periodic sequence, how do we obtain this DFS of a 2D sequence? The sequence what we had considered already, the same we have taken for these code demonstration as well. So the example, we have this 0 0 1 2 3 1 2 and 3, and this sequence is 0. Here it is 0, and this pattern is repeating in the both the directions, row wise and column wise, and it would continue to minus infinity to plus infinity in both the directions. So the fundamental period, and here you can see the command for getting the DFS. This is FFT2 and one dimensional sequence, that is FFT1, and here FFT2 of x, and you can specify the order also. FFT2 x comma 4 or 2, whatever the period can be specified, n1 and comma n2. So the 2-dimensional period can be mentioned for FFT2, and here this NUMELX is just the scaling. If you recall that it can be used in analysis equation or synthesis equation. Here it is not necessary. I just want to demonstrate that if you use the scaling here, it is possible to use it. There is the scaling, and this is just computing the numerical. So how many elements are there? That's going to be 4. So that's how this is not. Or you need to use it as n1 into n2. The period is known. What is the period for n1 into what is the period for n2? So that's how this FFT2 DFS is computed. Anyway, DFS is done for only one period. So create the mesh grid, that is from 0 1 0 1 here. K1 and K2 are the variables which is used here, and the points, and plot stem plot we get, and the real of x tilde. So get the real part of it, and because it's going to be a complex number, and then label them. So what we get is here 0 0, it is 1.5 and 0.5 minus 1 and 0. So this is due to the scaling. This value is 6. If you recall in the example, for this example we had the DFS as resulting in 6. So 6 by 4 it is giving this here 1.5, and then this is 1 by 2. This is again the divided value 1 by 4, and here also this is giving the value, and it is 0. So this is a scaled value. Otherwise the value what we had obtained in the previous lecture for this equations, analytically it would be same because of the FFT divided by this numerator NUMELS, that would compute the number of elements in the matrix and use it in the division. So that's not necessary. To show this an example that scaling can be used, this is given as 0, -1, 1.5 and 0.5. So this is a representation of the DFS of a 2D sequence K1 and K2, whose magnitudes or the amplitudes are given here, the value. So we can take the magnitude value and then do it here, because it's a this value is having the real only. So we got this values I plotted in this case. So this is how the DFS is obtained, H of n1, n2. But how do we separate this matrix into 2 sequences? So take the matrix, that's a 3 by 3 matrix, it is well known, X is equal to there, and then compute the determinant, check that determinant is 0. That for singular matrix, as we showed, this for separability concept is that can be done only for the singular matrix. If it is 0, display is a singular, otherwise non-singular, then you stop it here. And then find out this X and X transpose. Check if the X equal to X transpose. So for checking the square matrix, if it is symmetric or not. Okay, if it is symmetric, then go for 2 conditions. Absolute is 0, that is it is a singular matrix, and it is this equal, then separate into 2 parts, that is taking the columns alone, U of X of column alone and V is row alone. So this is, if you know the exact value, you can use it, otherwise you need not use this row. Take all the columns and 1 row. So that would give U and V separated matrices. Display U and V as such. Here this is U and this is V. So we can get this separability matrix from the MATLAB as well if we know the matrix of the 2D. So with this we have done the Fourier analysis of 1D and 2D, DSFT and DFS we have done. And how do we get these plots done? Using the FFT commands and IFFT commands of for 1D, and then FFT2 and IFFT2 is also useful in 2D sequences. And we have done this circular or periodic convolutions, and that can also be performed using the MATLAB. We'll see this example. We'll continue with the Fourier transform, that is discrete Fourier transform, in the next lecture. Thank you.